Hey everybody, welcome to 4.1, Approximating with the Tangent Line and Applications of Rates of Change. These two ideas are sort of sandwiched in the same section, even though they're really pretty distinctly different. So let me go over approximating with the tangent line first. He says, in many instances, finding the value of a function is difficult or impossible. With the use of calculus techniques, we can approximate the function value by finding a y value on a tangent line to the function. Since this method involves using a linear function, which is the tangent line function, at a nearby point, it is sometimes called the local linearization approximation. Okay, a lot of vocabulary in there. Let me just see if I can't sort it out for you. Here is the equation of my circle. There's the equation of my circle. And looking at it, by the way, I'm saying that if you didn't get taught much about circles, anytime you see an x squared plus a y squared with some other stuff being added or subtracted from it, you can pretty much guess that it's something called a conic section. And you might want to actually review that if you're ever going to be asked anything about pre-calc, because conic sections, it used to be a major part of algebra 2, and now it's just kind of pushed off a little bit to the side, saying, hey, we might cover conic sections in, say, for example, a 3+ class. So when I'm looking at this conic section, this particular one is a circle, and he says, let's look at this point 2, -2. And it's very important here that he gave you the whole point. A lot of times when I'm feeling lazy, I'll just say, well, x equals 2. But if I said that x equals 2, there'd be two spots. There'd be this spot and that spot where x equals 2. And you wouldn't know which one I was trying to find the equation of the tangent line for unless I told you what the height is. So here the height is -2. Here the height would be 0. So he wants us to focus on this lower dot, not the upper dot, because if I was looking at that upper dot, I'd want to find a tangent line that looked like this, and that would be different. And my approximations would be different as well. Speaking of the approximations, I wanted you to know I've graphed your circle and the equation. I'm going to get this equation, this blue equation. I'm going to get it for you in just a moment, but I'm going to use it right here, because what I'm saying is that these two things intersect exactly right here at 2, -2. But if I wanted to take an approximation nearby to 2, well, and say, for example, I didn't know how to take the derivative of this red function, it is going to use implicit differentiation. So it's legit for you to say that you're not sure that you do know how to find the derivative of it. If you could at least get that numeric derivative, which our calculator can do for us, then you could use that slope in order to find the equation of the blue line. And if I want to be on the blue line, notice right here, I could trace very close to that 2.0, very close, and say, hey, the y values there, those pop out for me. They're super close. I'm going to zoom in even more. Look at how close it is to the red line. So even if I'm right here, I've got a -1.718 as my y value, but over there on the red one, there, I'm pretty close to that. So, you know, the smaller the differences are, the closer we are, especially right around here somewhere. These numbers are super close, and they might be within your range of error. So if you're say a chemist and you need 3 decimal places of accuracy, well, then just go very close to the point that you're thinking of, and you will be able to find an approximate value for your red function there by using the blue function, right? So that's the equation of the tangent. And so that's what we want to do, is we want to find the equation of the tangent. And I know that this part, well, I tried to practice. I practiced here. This is going to be hard for me to do in this teeny little space. So I'm going to move over there. So I'm going to say that I have x squared plus y squared plus 2y equaling 4, okay? And I'm going to find the equation of my tangent using my cheat sheet. Remember, right here on the cheat sheet, I have finding the equation of a tangent. And so I've taken a snapshot of that and I'm putting it right here, and I'm going to do this process. So how do I go about finding the derivative? Well, this one, implicit differentiation, I can find the derivative. I don't need a calculator to do it, so I'm just going to do it. Let's practice implicit differentiation. Taking the derivative of x squared, I get 2x, and there's a dx here because I like to do that. And then taking the derivative of y squared, I'm going to get a 2y, and a dy dx happens to be the thing that I'm solving for. I'm going to take the derivative of 2y. I'm going to get 2, and don't forget the dy dx. And over here, when I take the derivative of 4, I will get 0. And I did take the derivative with respect to x, so there is a dx right here. And if you get into this habit where you're always writing these down every single time that you take a derivative, then you will never forget that that's what I'm solving for. And that these other things, they're just a byproduct. I don't really need them. Dx, to remember, dx over dx is equal to 1. And so a lot of teachers don't even teach that you need to do it. I teach it because if I don't remember to write down where I took a derivative, I'll legit forget what I'm looking for. What I'm looking for is to solve for dy dx. So what I'm going to do is I'm going to minus a 2x from both sides. And I'm noticing that I can factor that dy dx, and what am I factoring is this 2y and this 2. I see that I could factor a 2 out as well, but I'm not doing it right now because on the other side I have a negative 2x, and when I divide by my 2y plus 2, divide by my 2y plus 2. Yeah, then I can see that I could do some factoring. Dy dx equals negative 2 times x over 2 times y plus 1. These are going to cancel out, and my answer will be negative x over y plus 1. All of that was just me finding the derivative, okay? Now, boom. I did it. And also for number 1, I don't need to find the y's. He had to provide them to me just for me to be able to say I wanted to go to where x equals 2. And because it was that circle, I don't want to be up here. I want to be down here at y equals negative 2. So I've already got that value. And then I'm going to say, hey, when I find the derivative, what I'm doing is I am finding the slope, and in order to find the numeric value of the slope at this particular point when x equals 2, I'm going to do a dy dx. And note, I'm going to put in a 2 and a negative 2 right here into my notation to let you know that here was x, and I'm plugging in that 2 value, and here is y, and I'm plugging in that negative 2 value, and then I'm going to calculate it. And so I get a negative 2 over a negative 2 plus 1, which is a negative 2 over a negative 1, which is a positive slope of 2. And boy, howdy, that is my slope. Pretty easy to calculate. I'm glad he gave us this example, so we're hopefully following it. Now, I need to use this to create a linear equation. And I want to create my linear equation from, I don't actually have that on the mega cheat sheet. I hope you do still have it memorized. It's y minus y sub 1 equals m times the quantity x minus x sub 1. And if you look at these two formulas, you might feel like they're totally different. But let me explain. I think they're literally the same equation. And here's what I'm going to say. So he says plug in... let's find out what the value is that we're looking for at x equals 2 for us. And didn't I find the derivative at that 2? And shouldn't I just call that the slope? Yeah. And then look at this. So I'm supposed to take x and subtract an a. Well, that was the point that I was given. So I'm saying that when he gave me this problem, here, let me write it up here. I'm calling that x sub 1. I'm calling that y sub 1. But in our textbook, in the AP materials, in, say, your college textbook, what you'll notice is they might call this, ready, a, and they might call this f of a, as in pick a value for x, plug it in, we call that a, and then once we plug it in, we find out what our answer is, we call that f of a. And so I'll say that I could rewrite my equation now as y. Instead of y sub 1, I'm going to call it f of a. And instead of m, I'm going to call it the derivative at a. And then I have my x, and I'm taking away that initial point where I wanted to look, which I'm calling a. And boom, these two formulas now look extremely similar. Let me just add f of a to both sides, and you will now see that y equals f of a plus f prime of a times x minus a. And when Mr. Taylor says find the equation of the tangent and use it at x equals a, or if you can memorize this version of the formula, we are doing the same thing in both places. Okay, so now you know where my formula comes from. If you think you can memorize it, great. If not, then just on the memorizing, on the mega cheat sheet, use the notes, find the equation of the tangent and use it at x equals a. So now I'm going to finish this problem off, and I'm going to say that I had that slope, I had this x value, I had this y value, and so I will say that y equals, ready, f of a is supposed to be that -2, and f prime of a is my derivative at the point, and I got a value of 2, and then x, I was trying to look and see what was happening at 2. This is called the equation of the tangent. And it is worth writing those words when you do the AP exam, because then now I want to actually use this information. You're like, wait a minute, what were we doing again? Hold on, let's go back here. He says we want to use the equation of a tangent passing through this point to approximate a y coordinate. So instead of doing this, where I say, if I wanted to know what happens when x equals 2.1, normally I would do 2.1 and then I would square it, and then I would say y squared plus 2y equals 4, and I would figure out what that is, and I would subtract it, and then I would try to solve for it, and that would be basically a nightmare. I'd probably end up having to break out the quadratic formula. I definitely would need a calculator at some point. So no, I'm not going to do that. I'm going to use this approximate value. And I'm using it right here. Oh, I wish I had done this. I really love it when you remember to put an approximation symbol here, which is why if you can memorize that version of the formula, it's great. They don't take points off if you don't, but it's just helpful to you to remember that this is the approximation that you're doing. All right. So now he said, let's check to see what happens. Where was it again? When we get 2.1. So I'm now changing x, and I want to set x to be 2.1, and I'm going to plug it in right there. So I have 2.1 minus 2, and then I'm going to multiply that by 2, and then I'm going to take away 2 from it, and this is going to be the approximate y value that I'm looking for. When you do like 10 of these problems in a row, what you'll notice is a lot of times this isn't actually that bad. They're going to approximate fairly close to the value that you already have. And so like right here, 2.1 minus 2 is actually just a 0.1. And 0.1 times 2 is very easy. You follow that cute little trick where if you take 2 and you multiply it by 0.1, really all you have to do is do 2 times 1 and then move the decimal over once to get there. And so now I end up with y is approximately equal to -2 plus 0.2. So y is approximately, ready, -1.8. Ta-da! That's it. That's what you were being asked to do. And now you have that answer. Very easy to calculate. Right here, if I wanted x coordinate to be 1.9, let me change to my new color. I'm going to say that x is 1.9. So let's do this again and say that x equals 1.9. And so I had my original equation. Y is approximately equal to -2 plus 2 times, and here comes, I'm going to plug in my 1.9, and then I'm taking away 2. And again, notice right there, I get a fairly simple value. It's a -0.1. So I'm going to have the same thing as I did before. It's a 0.2, but this time it's going to be negative. And there was already a -2 in front. So a -2 in front I'm going to end up with y approximately equal to negative 2.2. Ta-da! Like I said, you got to do these several times, and you'll notice that this quantity here is never really as bad as you think it's going to be in order to calculate it. It's actually pretty easy. And so often this question will pop up in the no calculator activated section, because that's what the local linearization is supposed to do for you. It's supposed to give you a hands-on approximation that you can do, easy calculation without using a calculator. All right. Now that I've talked about that, let's just go over the process one more time. I'm going to say that x equals a. In this case, we're going to say that it's 2, and what I normally would have called x sub 1. I mean, now y sub 1, I'm going to call this f of a, and that is going to be, in this case, it's going to be 3. And then notice right here, he gave me the slope. So I can just plug this in. Y is approximately equal to, remember I'm supposed to put my f of a, and then I'm supposed to have a plus sign here, and then I've got my slope, which is a negative 2, and I'm going to multiply that, x minus a, and a happened to be a 2 again, and there we go. That's my approximation formula. In here, notice 2.01. You see what I'm getting here? There's a little trick here. So if that's what I'm going to plug in, 2.01, and then I take away 2 from it, I'm going to end up with 0.1, right? 0.01. And I'm going to multiply that by negative 2. And then I'm going to add 3 to it. And that's going to be my approximation. Let me finish it over here. And so I say that negative 2 times 0.01, we take this decimal, you move it over twice, and you get negative, so you get y is approximately equal to 3 minus 0.02, and so y is approximately equal to 2.98. Ta-da! Super simple. The rest of this section is about rates of change. Why do we need them? What are they important for? And so he's basically giving you another chance to work on some physics problems, because rates of change are very important in physics. Calculus is a math of change, so we are always wanting to know what's happening, how things are changing. And so I'll say that it seems like a weird place to put it, but I mean, it's an important topic to cover, and so that's why he went ahead and put it here. So he says the graph at the right models the rate of rainfall in inches per hour from midnight until 6 a.m. And this is during a tropical rainstorm. And I feel like he actually got this question from an actual AP free response question. So here's your graph. You got the rate of rainfall. You've got the time in hours per minute. And notice that this is a rate. So this is a graph of a derivative, right? We are graphing how things changed. And so that's important to note. From point A to point B, the slope is 0. It's a horizontal line. So he says, write a complete sentence to explain what point A on the graph represents. Please include numbers and units in your answer. And so the point just happens to be, this point A just happens to be 3 and 1. And 3 was in hours, and it's hours after midnight. So we're going to say, at 3 a.m., the rate of rainfall, and notice that I got these words right here, and I just put them into my sentence. The rate of rainfall is 1.0, and they're going to tell me right here what my units are, inches per hour. Ta-da! So let's see, this is my x value. We put x values in here, and there was my words for the rate, and then right there, these are my units, and make sure you put them in. And these sentences are the sentences that get you points on the AP exam. Now he says, what is the slope of the graph between points A and B? I already mentioned that. I was already noticing that slope was 0. And he says, please write a complete sentence to explain the meaning of our answer to example 4. So we're saying that we were starting at 3 a.m. and then we were going to 4 a.m. So between 3 and 4 a.m., the rate of rainfall is, ready? It's constant. What do you mean it's constant? How do I know that's constant? I told you this was the graph of a derivative. So it is telling you what the slope was at a particular moment in time. And so at a particular moment in time, the slope was 1.0. And then in the next moment, the slope was still 1.0. So what gives me a slope of 1 from two different places? Well, it must have been the slope, the original function was something like this. Ready? The original function was something like this. It had to be something like this. X equals 2. Because when you take the derivative of it, or x equals a number, that's what I meant to say. When I take the derivative of a constant, right, whatever that number is, I get a slope of 0. Do you see? So what is the slope of the graph between points B and point C? Let me see. I'm right here. Here's B, here's C, and I'm saying that I can do this. I could say that this first point is 4 and 1, and the second point is 5 and 0. This is my x sub 1, this is my x sub 2, this is my y sub 1, this is my y sub 2. And so if I want to find the slope between B and C, I would say that I have y sub 2 minus y sub 1 over x sub 2 minus x sub 1, and it works out like this. I've got 0 minus 1, and I've got 5 minus 4, and that ends up being negative 1 over 1, which is negative 1. Now, he's not mentioning it here, but use units always. And so what are my units? Well, the units on top, by the way, were inches per hour, and on bottom the units were just hours. So the way that you could write that is literally how I've done it, or you can do inches per hour like that. There's nothing wrong with that, okay? And then write a complete sentence. Oh, so I'm moving on to number 7. Write a complete sentence to explain the meaning of my answer to example 6. And he says, between 4 a.m. and 5 a.m., the rate of rainfall is decreasing. Why decreasing? Because I got a negative number. At the rate of 1 inch per hour squared. That's the final way you could write it. You could write it like this, you could write it like this, or you can write it like this. And this one's more common, but I just wanted you to show where they all came from. Now, I will usually get in class when I talk about this topic, I'll be like, do you have to use the word decreasing? The answer is no, but if you don't use the word decreasing, then you do have to use the negative. Can I use the word decreasing and use a negative? The answer is no. So an alternate sentence would be between 4 and 5 a.m. the rate of rainfall, terrible handwriting here, is, ready, it is negative 1 inches per hour squared. But not okay, do not write this, would be between 4 and 5, the rate is decreasing. at -1 inches per hour squared. We do not want to have a double negative here. No, make sure you don't do that. All right, good luck.